Hey guys and gals, it is Mr. Anderson one more time in section 8.1.3 talking about factoring with you guys. Today we're going to talk about some special products that maybe have a bit of a certain pattern that if you realize it, you can utilize it to save yourself a little bit of time. And so we'll talk about that. I'll expose you to it, but trust me when I tell you that all of these things are going to have the factorability with everything that we've seen in every part of the 8.1.1 and 8.1.2 videos. So one more time, if you haven't seen those, I can't advocate enough. Go back, check those items out because it's worth it. It's worth it to come into this with some understanding because it might answer some questions you didn't even know you had. All right, we've got a couple problems here. We're going to start with 8.24. And it says, factor these quadratic expressions. Use the diamond problem and the generic rectangle for 8.1. And I'll remind you guys of this in part A, how we're going to do this. And they say use both of these things. So I'll set up my generic rectangle. And my generic rectangle looks like this. Remember, we can put the first term in the lower left-hand corner. We can put the last term in the upper right-hand corner. And the idea here is that we've got a diagonal, and if we multiply 9 times x squared, that works out to be 9x squared. My other diagonal's got to be 9x squared as well. It has to have it as a product. Well, it can't be 1x and, no, I shouldn't say it can't be. Well, it can't be 1x and 9x because those don't add up to 6x. It's got to be 3x and 3x because it's the only thing that adds up to 6, but somehow also multiplies to be 9x squared. And what I'm going to point out here is that if I go ahead and start to factor this and say, okay, what kinds of things make x squared? Well, that's an x and an x. And what kinds of things make 9 that also make a 3? And when I multiply by x, well, it's going to be a 3 there and a 3 there. If I recognize outright that this is a perfect square, because x times x is x squared, that's a perfect square, and I recognize that 9 is a perfect square because 3 times 3 is 9, then look at what happens when I have this factorization. I've got x plus 3 from the bottom. I've got x plus 3 from the side, and that, of course, can be rewritten as x plus 3 because it's multiplied by itself, x plus 3 squared. So either one of these would be just fine as the factorization for that. Okay? As we move on to B, ladies and gentlemen, I'm going to slide this over. We're going to do this particular part of this one over here. And one more time, I'll use my generic rectangle. All right, I've got the 2x squared going here in the lower left. I've got the 3, my last term, going here in the upper right. And I recognize that 2x squared times 3 gives me 6x. Okay, so what I'm going to have to go ahead and do is I'm going to have to write here two numbers that multiply to be 6 that add up to be 5. Now, this for me is pretty nice and easy because the two numbers that multiply to be 6 and add up to 5 are already on my screen. Now, trust me when I tell you they're going to include the x because it does need to add up to 5x. Okay, so it's going to be 3x and 2x. And now, the way we write this is, the way we write the factorization is I'm not sure it matters a ton, right? 2x squared and 2x, well, that's going to be 2x and 1x, and then, of course, 2x times 1 is 2x, and then, of course, 1x times 3 is the 3x, and then, of course, finally, 3 times 1 is 3. And I guess I got to backtrack on something I said. It does matter. If I would have flip-flopped the 3 and the 1, this factoring would not have worked out. Okay, so how do I write this in factored form? This is going to be 2x and 3, and then finally 1x and 1. And some of you guys are wondering about, I'm sure, can I flip these two binomials around? Could I write that in the opposite order? And the answer, of course, is yes, and that has to do with the commutativity of multiplication. This would be the exact same thing as 1x plus 1 times 2x plus 3, and that'll work out. Okay, let's take a peek at one more of these, and I'll do this one in a different color so it stands out. Look at letter C with me here. I'll set this one up using my good old generic rectangle, and the generic rectangle requires me to put x squared here, my first term, requires me to put -7 here, my last term, right? I do include that sign, and so now I'm looking for two numbers that multiply to be -7x squared, and I'll write that down, and maybe I'll even use my diamond here, that multiply to be -7x, but they've also got to add up to be 5x. Okay, now here's what I recognize. They multiply to be -7x, but they've got to add 7x squared. I'm sorry, I missed the squared. But they've got to add up to be 5x squared. Here's what I know about 7. 7 is prime, and this means I have -1 and 7. This means I have -7 and 1, and I have no other options because 7 is prime. And granted, 7 is prime, -7 is not, so you see how I like include the negative on the 1 and the 7. And the question I guess I'd ask is which one of these adds up to 5x? And the answer is neither of them do. And this happens to us, right? This happens to us occasionally, and when we run into a situation like this, we've got to say this thing is not factorable. Okay, and that does happen. It's a real life thing, and don't be afraid to say that after you've exhausted all possibilities. But it's of course good to check and recheck to make sure it is in fact not factorable, rather than just jump right to that conclusion. All right, let's keep going here. We've got a couple more special cases. I'm going to try to tackle a couple of these that kind of yield a bit different of a result. What do you do in a situation like this when you've got something like part A that appears to be missing a term? Well, you've got a couple options here. One option is to rewrite it with the missing term with a coefficient of 0. So look at the way I rewrote part A. I said, what's the same as 9x squared minus 4 is 9x squared plus 0x minus 4. And then I can go ahead and start to filter this into my generic rectangle. Okay, 9x squared, -4. And now let's see, I've got two things that need to multiply to be -36x squared that add up to 0, right? And I recognize 36. I recognize that as a perfect square. What I mean is I know that that's 6 times 6. And here's what else I recognize. It's not positive 36, it's -36. And the only way to make it a -36 is to have one of those things be negative. Now check this out. 6 and 36, I'm sorry, 6 and -6, these things are opposites. And what that means for me is if I want -36x squared, I can get it with -6x and positive 6x. Sorry about that. And that works out really well because, of course, what do they add to? They add up to 0. All right, so what in the heck do we just have going on there? Well, I need the numbers that multiply to be 9x squared, and they're, of course, going to be 3x and 3x. The reason I know they have to be the same is because of the similarity of these two things. And then, of course, finally, the two numbers that multiply to be 4 are going to be 2 and 2, again, given the similarity of those things. Now, check this out real fast. 6x and 2, I'm sorry, 3x and 2, that makes 6x. Oops, I got rid of one more, 2. Shoot. And then, likewise, 3x and 2, that does make 6. Sorry, this is an x. Sorry about that. Okay, and that's good. That's good. That's exactly what we want. But now the question is, I'm trying to get rid of some of these items. I'm erasing too much. The question is, how do I make that 4 negative? Well, if the 4 and the 6x over here in that second column are negative, this 2 is going to be negative. And that will, of course, factor into this scenario, 3x minus 2, and then 3x plus 2. And notice how similar these two things are. They're not exactly the same, though. And when we run into a scenario like this, these are called the difference of squares case. Okay, so that's I don't want to say it's super common, but if you recognize that, the 9x squared being a perfect square, the 4 being a perfect square. Here's one perfect square, here is another perfect square, and here is your difference. Okay, so that could save you a little bit of time. All right, another scenario we've got, and we can tackle this, and I'm going to do more. Maybe you've seen, factoring a GCF out of a binomial in a previous course, but it works to use the generic rectangle here, and I'll try to do this one quickly here. One more time, I can write this as 12x squared minus 16x plus 0. Okay, that means the 12x squared goes here, the 0 goes here, and then, of course, multiply those two things together, and they need to kind of multiply to be 0. And that tells me that something here, one of these two things, the only way I can multiply and get 0 is if one of those things is 0. Something here needs to be 0. It has to be 0 or 0x or something like that. So be considerate of that as you're, how to put it, moving forward here. The way to do it is needs to multiply to be 0 and add up to 16x. And if I do this way, just put a 16x here and a 0 here, well, then that means this is going to be, let's see, it's got to be negative. It's got to be negative. That means I could use things like 3x and 4x. I'll put the 4x here just because I recognize 4 goes into 16. I'll put the 3x here. This is going to be 4x and 0. And then this would have to be 3x, and the way I get a negative 16 is with a negative 4. Okay, now you could write this as 4x plus 0. All right, you could write this as 3x minus 4. And does that work? Yeah. But the more common way to do this is write this as a monomial times a binomial. All right, something like that. Oh, I realized I was covered up there. Okay. The other thing that most people would probably advocate is for you to investigate the 12 and the 16 and say, hey, what numbers go into 12 and 16? And what can you take out? They obviously both have an x involved, so the x can come out. And 4 is your GCF, your greatest common factor, so 4 can be factored out as well. And sure enough, we validate that with the 4x there. Okay. Last thing I'm going to try to do quickly is there are some quadratics. In this case, we've got a quadratic trinomial that has more than one factoring. And the reason this is going to be the case is because 4x and 10x and 6, those are all products of the same scalar 2. So you could factor out a 2 ahead of time. In fact, that's what some people would advise. But you can also factor this using your generic rectangle, your 4x squared, your negative 6, and ladies and gentlemen, I've got 4x times negative 6, that's negative 24. We've seen a problem like this, negative 24x squared. We've seen a problem like this before. What two numbers multiply to be negative 24 that add up to negative 10? Now it's not 4 and 6 because the 10 is negative. It's actually going to be negative 12 and 2. Okay, now think about that. Obviously, I need x's here. Okay, now I can go ahead and start doing some thinking. I can say, all right, the factors of 4x, well, I can use things like 4 and 1, and then I need to get a 12 here, right? So 3, oops, not an x, sorry, 3 and 2, and now, of course, 3 and 2 makes 6, 1 and 2 makes 1x and 2 makes 2x, and 4x and 3 make 12, but the 3's got to be negative because I recognize this row is full of negatives, so that means this 3's got to be negative. So how could I go ahead and rewrite that? 1x minus 3, and then 4x plus 2. Recognize, too, that both of those things have a multiple of 2 in them. Okay, so I could have factored out that 2 redistributed here, so another factorization would have been, right, and that's just placing the multiple of 2 here instead, right? Some of you guys would have, like I said, started by factoring out 2. Okay, finally, a little bit more review preview, and there's just 3 problems that are associated with this assignment. They are 30, 31, and 32. Ladies and gentlemen, we're going to ask you to check these out, give them a shot, and start asking questions. Folks, I appreciate you watching. Have a great day.